All right, hello there. And what we're going to do in this video is look at two very important and related theorems in calculus. They actually are the backbone to a lot of things that we do later, even though they might not be mentioned as much. Excuse me. But we have the mean value theorem and we have Rolle's theorem. Now, you notice that they almost look identical, but Rolle's theorem is actually a special case of the mean value theorem. So let's take a look at what they say. So the mean value theorem says if f is continuous, and there should be an if here, it's kind of important. If f is a continuous function on the closed interval a to b, as you can see in the picture below, we're looking at a function between x equals a and x equals b, and differentiable on the open interval a to b, so it might not be differentiable at the endpoints, but that's okay. Then there is a value of c that's between a and b, such that, and the quantities, remember what those mean. So f prime of c means the derivative at c. So the derivative somewhere in the middle of the interval is equal to f of b minus f of a over b minus a. And remember that the geometrical interpretation of that is the average rate of change or the slope of the secant line between the two endpoints. So as you can see in the picture, we have the slope between the two endpoints of the graph. And then we also have the point between A and B where the tangent line has the same slope. So that's basically what the mean value theorem is guaranteed. And the practical application of this is speeding, believe it or not. So have you ever seen a speed trap on a highway or something, and maybe a car passes by the first cop and they're going 60 miles an hour and they think they're okay? And then they speed up, and then they see another cop another mile or so up the road, and they slow down to, say, 60 miles an hour again. But then the cop pulls them over, and they think, well, how the heck did they know that I was speeding? And well, if you sped up, they actually kept track of how far you went over a certain amount of time. And if your average speed was, say, 80 miles per hour, they knew that at some point you had to be going 80 miles per hour. So it's basically a theorem that says there is a point where the instantaneous rate of change is equal to the overall average rate of change. And that's why it's called mean value theorem, because slope changes as you go from one point to the other. There is an average in there somewhere, and somewhere in the middle is where those are equal. So we're going to see how that's illustrated in a little bit. Rolle's theorem is a special case of the mean value theorem because there's the added benefit, added condition, added criteria that f of a is equal to f of b. So they're straight across from each other. Okay, and as you can see in the picture there, what that basically says is if you think about the quantity f of b minus f of a, just like in the mean value theorem, over b minus a, well, if those two things are equal, if f of b and f of a are equal, then the numerator is 0. So that means we're basically saying that there's some point where the derivative is equal to 0, which means there's a horizontal tangent line, which mostly means that there's going to be a min or a max. And that's going to be kind of important to us later. Not all horizontal tangents are mins or maxes, but that's kind of where we get a lot of our important things. So, important thing, this is probably our first exposure to reading a theorem and understanding how to use a theorem. Anything that's after the word if is basically called your hypothesis. So what we're basically saying is all you need to know is that f is continuous and f is differentiable. For Rolle's theorem, you also have to know that f of a is equal to f of b, and then the conclusion is met. So what we're going to do is basically just all about showing that the conclusion is true, finding the value of c so that the conclusion is true. Okay, knowing that we have met the conditions that f is continuous and differentiable. And like I said in Rolle's theorem's case, that f of a is equal to f of b. So let's take a look at this. So I have the two examples side by side here. So what we're going to do, we're going to try to figure out which theorem actually applies by finding the values of the function, because we have to find them anyway. So our first function, f of x is equal to x plus 20 over x, and we're on the interval 0.5 to 10. And the first question you have to ask yourself is f continuous on the interval 0.5 to 10? And you just pause for a second because you think, well, wait a minute, it's undefined at 0, but 0 is not inside that interval, so we don't have to worry about that. So yes, f of x is continuous on that interval. And yes, f of x is therefore differentiable on that interval because there's no other kinks in the graph other than the asymptote when x is equal to 0. So it meets those criteria, okay? Now the added thing we have to check is, let's double check what f of 0.5 and f of 10 are, because that determines if we can use the mean value theorem or the oversimplified version of the mean value theorem, the Rolle's theorem, okay? So f of 0.5, if we plug in 0.5, I'm just telling you right now that we get 40.5. Plug in 0.5 for x, 20 divided by 0.5 is 40, and then add 0.5 to get 40.5. F of 10, however, is 10 plus 20 over 10, which is 12. Okay, so Rolle's theorem can't be used, but mean value theorem can be. And we know that there is a value of c in the middle of there somewhere because f meets the criteria. It is continuous and it is differentiable. So we compute two things. First thing we compute is f of 10 minus f of 0.5 all over 10 minus 0.5. In other words, that average rate of change. F of 10 is 12. F of 0.5 is 40.5. The difference between the x values is 9.5. We're getting a little nervous because now we're divided by 9.5. How could this come out to be a nice number, right? That's probably what you're thinking. I know I was thinking the same thing when I worked this out before. But this is negative 28.5 over 9.5. And would you believe it's negative 3? So that is our average rate of change between those 2 points. Okay, if you drew the graph and plotted the points where x equals 0.5 and 10 and drew the line between them, that is the slope of the secant line between those 2 points. Great. Okay. Mean value theorem says, hey, there's a value of c somewhere between 0.5 and 10, so that the slope of the tangent line is also equal to negative 3. Okay, so what we have to do, we have to find the first derivative. So f prime of x is equal to, well, derivative of x is 1. And the derivative of 20 over x, this is one of those, again, where it's very handy to know the derivative of 1 over x without having to go through and write it as x to the negative 1 and then find the derivative. I mean, if you're first learning it, that's one thing. But as you move through calculus, this is going to be a very handy derivative to know right off the top of your head. So it's going to be minus 20 over x squared. And we want that to be equal to negative 3. So when we solve this equation for x, or c as it were, it doesn't matter what letter you use really, we should get a value between 0.5 and 10, and that's illustrating the theorem. We're not proving it. We're not going to prove that in this course. That's a long proof. So let's take a look at what's happening here. So I am going to subtract 1 from both sides and get that. And actually, I'm going to move this over to the left. There we go. And then I'm going to multiply both sides by x squared and then divide both sides by negative 4, and we get 5 equals x squared, which means x has 2 potential values. We could be positive root 5 or negative root 5. Now, the thing is, positive root 5 is the one that's in our interval, negative root 5 is not. So that value of x, or like I said, c as it were, is what illustrates the theorem. That is the value where the slope of the tangent line is equal to the overall rate of change between the points. Okay, so that is the mean value theorem illustrated. Okay, and like I said, we know that value exists because it met the hypotheses, right? All it had to do was be continuous and differentiable, and we knew that this was a guaranteed to happen. Okay, now let's take a look at this other function over here. We have f of x equals x minus 10 root x plus 80. On the interval 16 to 36. Gee, I wonder why I picked 2 perfect square points. Well, let's see. So again, first question is f of x continuous on, oh, I wrote the wrong values. This is what happens when you copy and paste sometimes. Let me just update that real quick. We know we're looking at 16 to 36. So 16 to 36 and 16 to 36. Okay. So is f of x continuous on that interval? Absolutely. Square roots are only questionable, well, I should say undefined, when you're trying to plug in a negative number. We're not even going anywhere near negatives or even 0 because we know that the function's not differentiable at 0. But we're not worried about that. We're worried about the interval 16 to 36. So f of 16, well, what is that? So f of 16 would be 16 minus 10 root 16 plus 80. And when we crunch that out, we get 16 minus 40 plus 80. Looks like that's 56. f of 36, similar thing. So you have 36 minus 10 root 36 plus 80. 10 root 36 is 60. And would you believe that that is also 56? So you could apply mean value theorem. Mean value theorem will work for that. Rolle's theorem, remember, is just a special case where the two function values are equal. So if you have two function values that are equal at different points, somewhere in between them, as long as you have a continuous and differentiable function, somewhere in between them, you're going to have a horizontal tangent line. So we do the same thing. So we want f prime of x to equal 0. And again, this is Rolle's theorem. So what is f prime of x? Well, the derivative of x is 1. And again, another derivative that's handy to know, you probably have seen that already, is this derivative of the square root of x is 1 over 2 root x. And of course, I want to simplify that to 1 minus 5 over root x, okay? And I'm going to move that 5 over root x to the other side. And that means the square root of x is equal to 5, and that means x is equal to 25, and that is the value of x that guarantees the result. So it is inside the interval 16 to 36, just so happens to be the perfect square that's between them. That's kind of a fluke. So these are how these theorems are illustrated. And again, the guarantee is that there is a value. Our job is now just finding that value, okay? And just showing that it is in between A and B. So I hope you found this helpful. I want to thank you for taking the time to watch this video.